So now we're going to talk about moments of inertia. And another way to think about moments of inertia is they are the second moments. And this is because they invoke the squares of distances, right? And we have the definitions here. I'm just going to talk a little bit about what they are. I'm not going to derive them for you. But what we learned previously is that the first moments are going to tell us about balance. They're going to give us information about that center of mass, the centroid, right? They'll also give us information about torque. Torque is the twisting force which tends to cause the rotation. So we're taking all of these kind of, the center of mass and how much twisting needs to occur to find this moment of inertia. And what is inertia? When we think about the definition of what inertia is, the inertia is a state of just being, right? It's a state of rest. So another way to maybe reword this, because I keep saying the same thing, is it's a quantity that determines the torque needed for this desired angular rotation about a rotational axis. So maybe in more layman's terms, we can think about this moment of inertia is describing to us, it's measuring how difficult it is to change an object's current rotational speed. So maybe like something is completely still, and that moment of inertia, what is that rotational force you have to apply to get it started or to get it moving? Again, I am not a physics teacher, so go to your physics teacher for more information on specifically how the moment of inertia comes into play. And I'm sure as I have taught this class more, I will have a better explanation for you. But right now, that's the best I've got. And I'm going to say, hey, here are our three moments of inertia about the X, Y, and Z axis. And then also if we had a line R, which was not positioned on one of those axes. So these are our formulas for a 3D solid, and a two-dimensional plate looks very similar. If we compare, say, this X formula and this X formula, up here about the x-axis, we're talking about the sum of the squares. Here, when we're in 2D, we just do not have that z variable showing up. All right, so let's just jump in and do an example about how we would find this moment of inertia. So for this example, we're going to find the moment of inertia with respect to the y-axis. And we're dealing with a thin sheet or a lamina of constant density, and that's a constant 1 gram per centimeter squared. Remember, density is mass divided by area, bounded by this curve, y equals sine squared x divided by x squared, and the interval between pi and 2 pi on the x-axis. First things first, we want to think about what our graph looks like. And so sine squared x over x, it starts up here and it goes down, and then we just see this tiny little hump between pi and 2 pi. So I'm just going to redraw that. I had to zoom in on my graph in order to see that properly, but we get something, if we're considering this just from pi to 2 pi, that looks like that. And so we are interested in this region. So our moment of inertia about the y-axis, that's given by the formula, I sub y is the double integral of that region R. We have x squared, because that's part of the formula, delta dA. All right, so let's set this up and think about what our bounds need to be. Should we integrate with respect to x or with respect to y first? I would choose to integrate with respect to y first. That's going to make my bounds easy to set up. So my x values, we have x goes from pi to 2 pi. And my y values, we've got y goes from 0 to that curve, sine squared x divided by x squared. And then, of course, we have x squared, delta, and my dA is defined as dy dx. Of course, me as the math teacher, my job is to teach you how to set up these formulas and to make sure you know how to utilize them. Your physics teacher, your engineering teacher, they're going to get into you about why you need to be able to find this. All right, so here we go. We have pi to 2 pi. I'm actually going to go ahead and pull that delta out in front. And integrating x squared with respect to y, that's going to give me x squared y, which we need to evaluate from y equals sine squared x over x squared to y equals 0. So here I'm going to plug this guy in, and that's going to cancel my x squareds, and I plug in 0, it will cancel that term. So I have delta, the integral from pi to 2 pi of sine squared x dx. And then when we are faced with integrating sine squared x dx, we plug in one of our double angle formulas. I'm going to use the fact that sine squared x dx is 1/2, 1 minus the cosine of 2x. So pulling that 2 out in front, I have delta over 2, integral from pi to 2 pi of 1 minus cosine 2x dx. Each of these terms is easy for us to integrate. So I have x minus, that will be 1/2 sine of 2x. And of course, we're going to plug in x is 2 pi and x is pi. So I have delta over 2. Got 2 pi minus 1/2 sine of 2 times 2 pi is 4 pi. That's just going to give us 0. And then we've got minus pi minus the sine of pi. Again, that's going to give us, 1/2 of 0 is 0. So we end up with 2 pi minus pi. And this is just going to be pi delta over 2, or pi over 2 delta. And if we recall the fact that we know that this delta has a 1 gram per centimeter squared density, and if we think about this area we just found, area is normally going to be unit squared, so centimeters squared. We have that x squared to start with, so we have centimeters to the 4th times 1 gram per centimeter squared. So that gives us pi over 2 gram centimeters squared. That is my moment of inertia about the y-axis. So this has to do with the force required to get something moving, I guess to move this plate around the y-axis. I think that's the physics explanation. As always, email me with questions. Good luck, be safe, have fun.